We have talked about kinetic energy, the energy of motion. We've talked about work, how you give something energy or take energy away. And now we have potential energy. So my simple definition is when you do work to store energy due to position. So the two interesting aspects of this are store, it's a way to hold on to energy sort of, and then position, I could say arrangement would be more general, but for now we'll think about how it's the position of something that matters. So we're going to demonstrate it and think about it with this simple setup here. It's just a rod with a little board, right? And down here I have a mass, M, in what we'll call position A, and all I'm going to do is bring it up here to position B. Let's think about what happens if I do that. So here's the mass, and I lift it. Oh, it's so heavy, I can barely make it move. And let's think, what force am I applying to lift it? I'm applying mg. Right? Now I must be applying a little bit more than mg because it's moving up. But the way you can think about it is I'm moving it up at a constant velocity, a very slow velocity. The amount of acceleration it took to reach this velocity is essentially nothing. So basically, I had to exceed mg for just a teeny brief flash of time, but I'm basically applying a force mg. So that's why we say when we do some move like this, that when we lifted it up there, we were just applying the force mg. Okay, so I applied that force and I brought it up to this level. So that's sort of the displacement, right? We could call that delta y. Put a vector on it, it's a displacement. And the force I applied, Fp, the push force, is equal to mg. Technically, it had to be slightly more just for a brief instant to get an initial velocity going. But during this whole path, it was only Fp, and Fp is equal to mg. So let's see, the work to get the mass here is work equals, and then F dot ds displacement, right? So displacement vector is this way, the force is this way. It has the magnitude mg, so it's mg times delta y. Mg delta y. It's positive because I pushed and the displacement's in the same direction. Okay, so now it's at B. And at B it doesn't have any kinetic energy, right? But it has something, because what if I do this? It picked up quite a bit of kinetic energy, right? When it hit the table, it had a lot of kinetic energy. So you could also say at B, position B, it might fall. Right? It has the potential to gain kinetic energy, like if someone pushes it off. Due to its position. Or another way to say that is it has potential energy. So you might be able to see now in my definition these two aspects. It's the position that gave it the potential energy. We pushed it up to this high level, and when it fell, it could get its kinetic, it could convert it to kinetic. And it was storing it because what was sitting up there, it was holding on to this potential energy, which it gave up as it fell. So if we're going to write the potential energy, in this case where the work was done against gravity, we could call it U subscript G. So we'll use that to mean gravitational potential energy. And this also is when you're near the Earth. We'll say it's equal to mgy. Right? Mgy if it's equal to 0 at y equals 0. Potential energy is one of these values that's always a change, it's always a difference. Its value depends on what you consider 0. That's why I contrast it to kinetic, where I said kinetic was absolute. Kinetic energy is 1 half mv squared. It doesn't matter where the origin is. Potential really depends on where the origin is. So in this example, we put the origin here at the table, and we said it builds up some potential energy, mg times this difference in height. But in the demo you saw we could define another origin down here on the floor, right? The weight actually fell even lower. So you could call that 0 and you get a different potential. But the potential differences are always the same. It always depends on the difference between two heights. One of the most fundamental concepts in physics is energy conservation. In the universe, there's a certain amount of energy, and it can never go up, and it can never go down. It can never be created, it can never be destroyed. So this sounds like a pretty simple concept to use. It gets a little tricky because there's a lot of different kinds of energy, and the universe is kind of big. So what we do in intro mechanics is we define something we call the mechanical energy. So the mechanical energy just means the energies that we've talked about so far in this class. It's equal to the sum of the kinetic energy that we've talked about plus the potential energy. And for now I'll put a G on there, meaning just the gravitational potential energy. So the idea is if you take an object or a system and you calculate kinetic plus potential, that will be constant. But we don't want to do the whole universe. We just want to do part of the universe. So we say for an isolated system. So maybe the system is just the object you're considering, or maybe it's two objects. Okay? So by isolated system, let's clarify a little bit there. We really mean that there's no external work. Or well, we don't mean there's no external work. We mean that this will be constant if there is no external work coming into the system. And while we say constant, we mean this part, the whole thing is constant. So you can transfer between K and U. So in your system, you can have the potential increase and decrease, the kinetic increase and decrease, but their sum is equal to the mechanical energy and it's constant. Okay? So this is a fairly simple idea. You'll see it written different ways in books. Because it's a constant, we think of it in terms of changes a lot. So another way to say this is that the change in mechanical energy is 0. Same thing, right? If it's constant, that means we could write it this way. The final mechanical energy minus the initial mechanical energy is 0. You could even write it this way. You might see it written this way. The final mechanical energy equals the initial mechanical energy. So you can see we're just doing a little algebra, writing this all these different ways. They all mean the same thing, is that the mechanical energy is constant. You can even break it up into these two. So maybe you'll see it written this way. Let's see, if the change in mechanical energy equals, let's see, the final minus the initial, we already wrote that, right? So the final mechanical energy is the final kinetic energy plus the final potential energy. I'll leave off the gravitational G for now, we'll just call it UF. And that would be minus the initial kinetic energy, minus the initial mechanical energy. So initial K plus initial I, right? And that must be equal to 0, right? Oh, then if you rearrange this a little bit, you see that it's equal to the final kinetic minus the final initial plus the final potential minus the initial potential equals 0, which means that the delta K plus, delta U equals 0. So this is another way you'll see this statement written quite a bit. These are all saying the exact same thing, is that if nothing comes in and does external work, then this total energy will be the same. So you can think of it as the total energy, you can think of it as the small changes between the kinetic and the potential. You can also see this one as how we have this transfer. Maybe this goes up and this goes down. Then we transferred some of our kinetic energy into potential energy. So the idea to apply it to a problem is often actually intuitive. You don't have to go through this thought process. But when you see it written in books in these various forms, you'll often see that one, you'll often see this one. But to make sure you understand, really, these all mean the same thing. Let's test our conservation of energy formulas with the bowling ball. What we're going to do is let it swing from here. We're going to hold it still and let it swing to here. This is going to be the initial state. This is going to be the final state. Let's see. So the question is, at the end, how fast will the bowling ball be going? The best formula in this case is this one, delta K plus delta U equals 0. Whatever change in kinetic and whatever change in potential have to cancel out. So we would say, well, delta K is K final minus K initial. K final is what we're looking for, 1/2 mv squared. K initial is 0, because I'm going to release it from rest. So V is 0, so kinetic energy is 0. Plus U final, right? So the potential energy final, I'm going to let it be down. That's its lowest point, is what we're considering. And I'm going to measure, I've already measured, the height of the bowling ball, the center of the bowling ball above the ground, or above the table, is 0.16 meters. 0.16 meters. So this one would be mg 0.16 meters. We'll just use the y position above the table. Let's see, that's U final minus U initial is mg. And what I'm going to do is I'm going to hold it up in the air and release it from a height of 0.76 meters. Right, so minus mg 0.76 meters. All that should equal 0. And the only variable in here we have, let's see, we have v, that's what we're looking for. Each term has an m, and it's equal to 0, so we can basically cancel the m's. M's go away. Right? And we know g, so we can calculate v. So let's see, we could rearrange a little bit. 1/2 v squared plus, we could go ahead and pull the g out, and it's g times 0.16 minus 0.76 is minus 0.6 meters equals 0. All right. So then we could say 0.6 g on that side and bring in the 2, and v squared is 1.2 g. And if you finish it off, you get that the v should be about 3.4 meters per second. Something like that. So let's see if we get 3.4 meters per second. So here we go. I'm going to hold it, I think about here is about where it was at 0.76, right there. It's sitting at 0.76. So pull this out and let it go. And we look with the slow-mo camera, and sure enough, 3.4 meters per second. There's another way we can demonstrate the conservation of mechanical energy with our bowling ball, and that is to, let's see, release it over here. We'll call this the initial. Let it swing, see where it goes, and it's going to end somewhere around here, the final. Let's apply conservation of energy to that. That would be delta K plus delta U equals 0 is the convenient formula. And we're thinking this is the initial and the final, and this is the point where it stops. It swings up, stops to go the other way. So at both positions, it's at rest. So the final kinetic energy is 0, and the initial kinetic energy is 0, because the velocity is 0. For the height, we'll say we started it above the ground at some height yi, and we'll say it's going to end up at some height yf. So the potential energies, our final is mgyf minus initial mgyi. And all that has to equal 0. So you can see where we're headed here, 0, 0, 0. Bring this over here, and you get mgyf equals mgyi. Cancel, 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 cancel. And you get that it must end at the same height that it started, because we have to conserve energy. Right? If there's no kinetic involved in these two positions, then you have to have the same potential energy, and it has to be at the same height. We could go a little further and say, what if we started here, went to here, and then let it come back to here? What if we made, and then say it'll stop, and we make that the final state, initial final. Then we would have an initial height yi, a final height yf, but the same argument would apply. It would have to end up at the same height it started at, which leads to one of the most popular demonstrations in intro mechanics. So what I'm going to do is crawl up here and hold the ball against my face and release it. And if it obeys conservation of energy, it'll come to the exact same height and I'll be fine. It could go higher and then it would crush my face, but it's not going to because it's going to obey conservation of energy. Now I really don't like this demo because to me there's not a lot of dramatic tension because one, I know you've seen this before, you've seen it done before. And two, if a physicist gets their face messed up, does it really matter, you know? So I think what I'm going to do it different. I'm going to raise the stakes. Or you might say, I'm going to lower them. I'm going to do it from here, and I'm going to hold it here. So I cannot possibly back up any farther. I'm hanging off the edge of the bench. And I'm going to hold it here and release it. I give you the Hafner's cradle. I'm not nervous at all because I believe in the conservation of energy. We can now apply our conservation of energy ideas to the ball on the loop. So if I release it from here, probably not going to make it. No, but if I release it from way up here, I think it's got a chance. There it goes. So now let's calculate how high we need to release it from so it'll make the loop. Let's see, so we draw our loop, something like this, like that. And we want to know how high to put it here so it'll make it around the loop of radius r there. So you might look at it at first and say, well, let's see, I know what's going on. I would say it needs to be here, right? The same height. It'll be one guess. But you got to keep in mind, we don't just need it to get up here, we need it to stay on the track. And to stay on the track, it has to be going a certain speed. We don't want to just get the ball this high, we want to actually get it to make the entire loop. So you may recall, thinking back, we need a minimum speed back on the circular motion part. V equals the square root of g times r. Remember, that was the speed it took, over hill and under hill, to stay on the track. Square root of gr. So when we get here, that's the speed we need to be going. So where would we start up here? What height up here? Y initial, and we'd end up at a height here, Y final, and end up with a kinetic energy that's equivalent to having square root of g times r. Well, all we got to do is apply delta k plus delta u equals 0. Delta k plus delta u equals 0. Let's see, the final kinetic energy has to be 1/2 mv squared, right? 1/2 m, and the square root of gr squared is just gr, so right. Gravitational constant times r, or acceleration due to gravity times r. And minus the initial kinetic energy is 0. So I'm going to release it from rest. All right. And let's see, the final gravitational potential energy is mg times 2r plus final mg2r minus initial, which is mg, and then the height we're looking for, yi, minus mg y initial equals 0, like that. All right, then we just do a little bit of algebra and we see if we can solve for this height here. Let's see, mass is in every term. Mass goes away, very nice. And let's see, so we've got, I need to solve for yi. G is in every term. I knew something else was going to go away. G cancels. So we have 1/2 r plus 2r minus y initial equals 0. So right away you see that y is 3/2 r, or is 5/2 r. yi is 5/2r. Or you could think of it as it's 2r, the diameter of the circle, and it's another 1/2 of r above the top. So according to that, if we release it from that height, it should just barely make it around the loop. So let's see if that height works. Let's see, we get it back out. Here's the ball. Now I've marked it off. You got to kind of consider the position of the center of mass of the ball here and here. That's the circle, and then another radius up is about here. All right, so let's let that go. And look at that, not even close to making it around. What is wrong with the conservation of energy? Nothing is wrong with the conservation of energy. There might just be other forms of energy. So I'll let you think about what else might be going on here. If you can't get it, don't worry about it. I'll give you one hint. We'll reveal it in the second part of the class.